In this video, we're going to practice some strategies for integration using the various techniques we've learned in Calculus 2. First, we want to be sure that we've memorized our basic integration formulas. From there, we'll use the following guidelines for integration. First, use your memorized basic integration formulas. Sometimes they won't be obvious and you'll have to manipulate the integrand algebraically or with trigonometric identities. From there, you want to classify the integral by form. Look for u substitution. We usually choose u to represent the inner function of a composite function. Integration by parts, which is used for integrating certain products of two functions, and is often used for integrating logarithms and inverse trigonometric functions. We're going to look for powers of trigonometric functions, in which we'll rewrite the integrand in such a way so we can use trigonometric identities and u substitution. We'll use trigonometric substitution when we see expressions of one of these forms here, often with a root involved. And finally, when the integrand contains a rational function, we'll often want to use partial fraction decomposition. If we're still stuck at that point, we're going to want to try again using some less obvious techniques. Sometimes we use one of the techniques above along with substitution. Sometimes we'll need to multiply the integrand by an expression that's equivalent to 1, such as a conjugate over itself, that will then allow us to do a substitution or some other technique. In other cases, we might need to use completing the square, so that one of the techniques above may be used. And in yet other cases, we might need to rationalize the denominator, so we can use one of the techniques that we know. At this point, go ahead and pause the video and try each of the problems on your own first. Even if you get stuck, try the problem again using one of the other methods described here. If you're still stuck after that, then refer to that problem in the video to see one possible solution.
Number 1, the integral of cosine x over 1 plus sine squared x dx. Here, let's notice that we have a cosine x dx in the numerator, and we know that the derivative of sine is cosine, so we should be able to do a u sub if we let u equal sine x du equals cosine x dx. And this integral becomes 1 plus u squared in the denominator, and our cosine dx gets replaced by a du. We recognize this as tan inverse of u plus c, which will give us tan inverse of sine x plus c. Number 2, the integral from negative 1 to 1 of e to the tan inverse y over 1 plus y squared dy. Again, we want to look for a u sub, and hopefully we remember that the derivative of tan inverse y is 1 over 1 plus y squared. So if we let u equal tan inverse y, du is equal to 1 over 1 plus y squared dy. Now we look at the limits of integration. When y equals 1, u is equal to tan inverse of 1, which is equal to pi over 4. When y equals negative 1, u is equal to tan inverse of negative 1, which equals negative pi over 4. So our integral becomes the integral from negative pi over 4 to positive pi over 4 of e to the u du. That gives us e to the u evaluated from negative pi over 4 to pi over 4, which gives us e to the pi over 4 minus e to the negative pi over 4. Number 3, the integral of sine squared x cosine cubed x dx. So here we notice that we have an odd exponent on cosine, and so we'll go ahead and save one cosine x along with dx so that we can substitute using a Pythagorean identity and then u sub. So we have the integral of sine squared x, cosine squared x, cosine x dx. Now we'll go ahead and replace our cosine squared x with 1 minus sine squared x cosine x dx. Now we can let u equal sine x, du becomes cosine x dx, and we now have the integral of u squared times 1 minus u squared. Cosine x dx is a du, and we end up with u squared minus u to the 4th du. The antiderivative will be 1/3 u to the 3rd minus 1/5 u to the 5th plus c. Finally, we bring back sine to get 1/3 sine cubed x minus 1/5 sine to the 5th x plus c. Number 4, the integral from 0 to 1/2 of x over the square root of 1 minus x squared dx. Again, we'll go ahead and try u sub. If we let u equal this inner function here, we get that du is equal to negative 2x dx. If we multiply both sides by negative 1/2, we get x dx. Changing limits of integration, when x equals 1/2, u is equal to 1 minus 1/2 squared, which is 1/4, which gives us 3/4. When x equals 0, u is equal to 1 minus 0 squared, which will give us 1. So this integral becomes negative 1/2, the integral from 1 to 3/4. Our x dx becomes negative 1/2 du, so we have a du back here. And then in the denominator, we have the square root of u. We can get rid of that negative sign and switch the limits of integration like this. We have u to the negative 1/2 du. Finding the antiderivative, we get something like this. This gives us u to the 1/2, evaluated from 3/4 to 1. It's going to be 1 to the 1/2 power, which is 1, minus the square root of 3/4, which is root 3 over 2. We can make a common denominator and rewrite it this way. Number 5, the integral of the square root of 9 minus x squared over x dx. We notice in the numerator that we have the square root of 9 minus x squared, which is one of our forms for trigonometric substitution. So we're going to go ahead and let x equal 3 sine theta. So dx is equal to 3 cosine theta d theta. Our triangle will look something like this, where we have theta here. And sine theta is x over 3, so we have x here, 3 here, and down here we have 9 minus x squared. The square root of 9 minus x squared is equal to 3 cosine theta. So now this integral becomes 3 cosine theta is replacing our square root of 9 minus x squared. Our dx gives us another 3 cosine theta d theta. And in the denominator, we have just x, which is 3 sine theta. So this becomes 3 cosine squared theta over sine theta d theta. We can rewrite the numerator as 1 minus sine squared theta over sine theta d theta. Now we'll split that rational function like this. And now we just need to integrate cosecant theta minus sine theta d theta. The integral of cosecant is ln absolute cosecant theta minus cotangent theta. Now the antiderivative of negative sine is positive cosine theta, but we have to make sure we've distributed that 3 plus c. Now we've got to bring back our x's. So looking at our triangle, we notice that cosecant theta is equal to 3 over x. Cotangent theta is equal to the square root of 9 minus x squared over x, like that. And so we end up with 3 ln 3 over x minus the square root of 9 minus x squared over x plus 3 cosine theta is equal to the square root of 9 minus x squared plus c. Number 6, the integral of x to the 4th over x to the 10th plus 16 dx. This one might not be very obvious, but what if we rewrote it this way first? Instead of x to the 10th, we write x to the 5th squared plus 16. Now, if we let x to the 5th be u, then we notice a couple of things. First of all, we notice that du is 5x to the 4th dx, and 1/5 du is x to the 4th dx. So we've got our numerator taken care of. We also notice that we're going to have u squared plus a constant squared in the denominator, and that's something we know how to integrate. So this is going to become 1/5 the integral of u squared plus 16 in the denominator and a du in back. 1 over u squared plus a constant squared is tan inverse. So we get 1/5. We have 1 over the square root of that constant, which is 4, tan inverse of u over that 4 again, plus c. This becomes 1 over 20. Tan inverse, bring back our x to the 5th for the u, and we have it. Number 7, the integral of cotan x ln sine x dx. Here, if we let u equal the ln of sine x, du will be 1 over sine x times the derivative of the inner function, which is cosine x dx. And of course, we recognize cosine over sine as being cotangent. So this simply becomes the integral of u du, which will give us 1/2 u squared plus c, which is equal to 1/2 the ln of sine x all squared plus c. Number 8, the integral of the square root of 1 plus x over 1 minus x. There's more than one way of going about this. One possibility is to rewrite it as the root on top and the root on the bottom, and then multiply to get rid of one of these roots. If we multiply down here by 1 plus x under a root and the same thing on top, the numerator simply becomes 1 plus x. In the denominator, we have the product of 1 minus x and 1 plus x, which is 1 minus x squared, like this. Now we can split this up into two integrals. We have the integral of 1 over the square root of 1 minus x squared dx plus the integral of x over the square root of 1 minus x squared dx. The first integral is sine inverse, and the second integral turns out just to be the square root of 1 minus x squared. That second integral can be done with a u substitution, or you can reverse engineer it. Number 9, the integral of x to the 9th e to the x to the 5th dx. When we see exponentials with functions in the exponent, we're usually going to do u substitution. So we're tempted to start here, and then we notice that du is equal to 5x to the fourth dx. So 1/5 du is equal to x to the fourth dx. But we have an x to the ninth here. So if we think of this as x to the fifth e to the x to the fifth times x to the fourth dx, we notice that we have x to the fifth, which is u. We have e to the u, and x to the fourth dx is going to be du with a 1/5 in front. Now we can do integration by parts, which is going to turn out like this. U, e to the u, minus u, plus c. Now we bring back our x to the fifth, and there it is. Number 10, 1 over the quantity x plus 4 root x plus 1 dx. Let's try letting u equal the square root of x plus 1. That means that u squared is equal to x plus 1, and 2u du is equal to dx. So now we can rewrite this as the integral 2u in the numerator du, and in the bottom we have that x plus 4. Well, if we take this and add 3 to both sides, we get u squared plus 3 is equal to x plus 4. So here we have u squared plus 3, and then we have plus 4 times the square root of x plus 1, which in this case is just u. Now if we rearrange these terms, we'll have 2u on top still. We'll have u squared plus 4u plus 3 du. Now we can factor the denominator like this. And now we can do a partial fraction decomposition. So this will result in two equations. A plus b has to equal 2 because 2 is the coefficient in front of u, and then a plus 3b is equal to 0. Solving this system of equations, we find that a equals 3 and b equals -1. So now our integral becomes 3 over u plus 3 minus 1 over u plus 1 du. Integrating, we get 3 ln absolute u plus 3 minus ln of absolute u plus 1 plus c equals 3 ln, bringing back our root x plus 1. Here we'll have 3 plus root x plus 1 minus the ln of 1 plus root x plus 1 plus c. Number 11, the integral of secant squared x over the quantity tan x plus tan squared x dx. Oftentimes it's best to try u substitution first, and since we know that the derivative of tangent is secant squared, choosing u to be tan x seems to make sense. So we have du is equal to secant squared x dx. And we can rewrite this integral as 1 over u plus u squared du. We can factor the denominator like this. And now we notice that we have two linear factors in the denominator, so we'll go ahead and do partial fraction decomposition. So we have that a equals 1 and a plus b is equal to 0. This implies that b is equal to -1. So our integral becomes 1 over u minus 1 over 1 plus u du. Integrating, we have ln absolute u minus ln absolute 1 plus u plus c. Now we bring back our tangent. And that's it. Number 12, the integral of x minus 1 divided by x squared minus 4x plus 5 dx. So first notice the u substitution won't get us there. Even if we made u the denominator, du would not result in the numerator, unfortunately. So the next thing that seems logical here would be a partial fraction decomposition. However, we can't factor the denominator. So what we're going to do is we're going to manipulate the denominator in such a way so we can do a u substitution and then allow us to use one of our techniques. So if we look at the x squared minus 4x and complete the square just on that, that means we'll be adding 4 and subtracting 4. Now, if we just factor this, we get x minus 2 quantity squared, and the -4 and the 5 give us a positive 1. Now we can try our u sub if we let u equal x minus 2, du is equal to dx. And from here we notice that we can get u plus 1 equaling to x minus 1 for the numerator. So our integral becomes u plus 1 over u squared plus 1 du. Let's split this up into two integrals. For the first integral, we can do a u sub. It's going to give us something like this. You can pause the video and check that out. And in the second one, we have a tan inverse. Finally, we bring back our x minus 2. We could go ahead and multiply this out, and we get a result that looks like this. Number 13, the integral of ln of 1 plus x squared dx. We could try u sub, but it's not going to get us very far because we're going to end up with a du equaling 2x dx, and we don't have a 2x factor here. So the next thing that comes to mind is probably integration by parts, because we did that quite a bit with ln's when we were working on that technique. So if u is equal to ln of 1 plus x squared, and dv is equal to dx, du is going to equal 1 over 1 plus x squared with a 2x from the chain rule in the numerator, dx, and v here is just going to be x. So this integral is going to become, we multiply here, uv is going to give us x ln of 1 plus x squared minus the integral of what we get multiplying this way, which gives us 2x squared over 1 plus x squared dx. Now we notice that this rational expression has the same degree polynomial in the numerator and in the denominator. So we could do long division to rewrite the integrand and then integrate. But another way we can do this is we can put the 2 out here, which leaves us with just the x squared in the numerator. We have x squared plus 1 in the denominator. And we could write plus 1 minus 1 in the numerator like this. That's going to allow us to rewrite this integral as x squared plus 1 over x squared plus 1 dx minus the integral of 1 over x squared plus 1 dx. And of course, this is just 1. And here we'll have a tan inverse. Number 14, the integral of 3x squared minus 2 divided by x squared minus 2x minus 8. Here we notice that the degree of the numerator is the same as the degree of the denominator. So we're going to go ahead and rewrite our integrand using long division. So now our integral looks like this. Now we'll split this up into two separate integrals. So we have the integral of 3 dx plus the integral of 6x plus 22 over x squared minus 2x minus 8 dx. And with that second integral, we'll go ahead and do a partial fraction decomposition. So first we'll factor. We notice that we have two linear factors in the denominator. So we'll go ahead and do the shortcut on this, where we're going to let x equal negative 2. So the left-hand side becomes negative 12 plus 22. And on the right-hand side, this term will zero out because we're plugging in negative 2. And we get b times negative 2 minus 4. This will give us a positive 10 equals negative 6b. So b is equal to 10 over negative 6 or 5 over negative 3, like that. If we let x equal 4, then the left-hand side becomes 6 times 4, which is 24, plus 22 equals, this time this term will zero out, so we're only left with a times the quantity 4 plus 2. This gives us 46 equaling 6a, and so a is equal to 46 over 6, or 23 over 3. So now we're going to plug in our a and our b into here, giving us an integral that looks like this. Let's rewrite it one more time, writing the constants out in front. So we have the 23 over 3, the integral of 1 over x minus 4 dx. And then we have the minus sign from that 5/3, integral of 1 over x plus 2 dx. Here we have 3x, taking that integral, plus 23 over 3 ln of absolute x minus 4 minus 5 over 3 ln of x plus 2 plus c. Number 15, the integral of 1 over x times the square root of 4x squared plus 1 dx. So we're probably recognizing pretty quickly that under the square root we have this 4x squared plus 1, which makes us think of trigonometric substitution. I like to start off by rewriting this so I have a quantity squared, in other words 2x squared, and then I can do a u sub that will allow me to then continue on with a trig sub. So let's first set u equal to 2x, du is equal to 2 dx. So half a du is equal to dx. We also notice from this that x is equal to 1/2 u. And so we can rewrite our integral putting a half du like that, and then the x there is 1/2 u, and we have the square root of u squared plus 1. The 1/2s cancel, and we end up with 1 over u square root of u squared plus 1 du. Now we'll go ahead with our trig sub. So we're now going to let u equal tan theta, du is equal to secant squared theta d theta. Drawing our triangle, tan theta is u, so that's opposite over adjacent, and here we have the square root of u squared plus 1. The square root of u squared plus 1 is going to equal, well, we know that if we use the adjacent and the hypotenuse, cosine of theta would be 1 over the square root of u squared plus 1, so secant theta equals the square root of u squared plus 1. And so now we can go ahead and rewrite this integral. Our du is a secant squared theta d theta. In the bottom, we've got u, which is tan theta, and the square root of u squared plus 1 is secant theta. Simplifying, we have the integral of secant theta over tan theta d theta. Simplifying even further, we know this is 1 over cosine theta. Here we have sine theta over cosine theta. If we multiply top and bottom by cosine, we'll get 1 over sine, which is the integral of cosecant theta d theta. The antiderivative of cosecant is the ln of absolute cosecant theta minus cotangent theta plus c. Now we're going to go look at our triangle again. We know that the sine of theta is opposite over hypotenuse, which means that the cosecant would be the reciprocal. So cosecant theta will be the square root of u squared plus 1 over u. And we know that the tangent of theta from way back over here is just plain u, so the cotangent would be 1 over u, like that. And now our last step is to replace u with 2x from the very beginning of our substitution. And that's going to give us something like this. Number 16, the integral of 1 over e to the 3t minus e to the t dt. A good habit to get into with a lot of these integrals where you're not sure how to start is to think about what a u substitution would do. And if you notice, if we think about u as being e to the t, then we could potentially get this to the point where we have something like this. And as soon as we get that, then we immediately think about partial fraction decomposition. So let's go ahead and give that a try. If we make u equal to e to the t, then du is equal to e to the t dt. And at this point, we feel kind of stuck, because even though we have a u to the third minus a u in the bottom, we have no place to deal with this, right? So there's another way of approaching this. If we go back to our equation of u and rewrite this in logarithmic form, we would have t equals ln u. And now we could say that dt is equal to 1 over u du. And so now we can rewrite this integral. Instead of dt, we're going to put 1 over u du. And then we have u to the third minus u, like that. From there, we can factor out a u to get u squared times u squared minus 1 du. And of course, we can keep factoring and write that as 1 over u squared, u plus 1, u minus 1 du. Now we're ready for partial fraction decomposition. We have a repeated linear factor of u, so we're going to write a over u plus b over u squared. Then we have our non-repeated linear factors like this. So making common denominators, we have 1 equals this term here needs to be multiplied by u and u plus 1, u minus 1. So that's u squared minus 1. So we get a u squared minus 1. The next term, b, will need to be multiplied by u squared minus 1. C will be multiplied by u squared and u minus 1. And finally, d needs to be multiplied by u squared and u plus 1. Distributing, we get a u to the third minus a u plus b u squared minus b plus c u to the third minus c u squared plus du to the third plus du squared. Now we'll group our like terms. So our terms with u cubed, we have an a, we have a c, and we have a d. Our squared terms, b minus c plus d. There's one linear term and one constant term. So a plus c plus d equals 0. b minus c plus d is also 0. Negative a is 0. And negative b is equal to 1. So that means that a is 0, b is negative 1. If we combine these two, we'll end up with a plus b. The c's cancel, and we have plus 2d equals 0. A is 0, b is negative 1. So we have d is equal to 1/2. From there, we can plug back into one of the original equations, and we'll notice that c is equal to negative 1/2. So now we rewrite our integral, plugging in a, b, and c into here. We have 0 over u, so there's nothing to write there. And then we have negative 1 over u squared plus c is negative 1/2 over u plus 1 plus d is 1/2 over u minus 1. This gives us negative the integral of u to the negative 2 du minus 1/2 the integral of 1 over u plus 1 du plus 1/2 the integral of 1 over u minus 1 du. It's going to give us u to the negative 1 minus 1/2 ln absolute u plus 1 plus 1/2 ln absolute u minus 1 plus c. Bringing back our e to the t, we're going to have 1 over e to the t minus 1/2 the ln of e to the t plus 1 plus 1/2 ln e to the t minus 1 plus c. This is a difference of two ln's, right, if I switch the order, so we can rewrite it as the ln of a quotient. Number 17, the integral dx over the square root of x plus 1 plus the square root of x.
This one isn't immediately clear how to start. If we notice, we have a sum of square roots in the denominator. So let's see what happens when we multiply by the conjugate on top and on bottom. This becomes the integral, the square root of x plus 1 minus the square root of x all over. We're going to get x plus 1 when we do the first multiplication. Multiplying here and here, we get the exact same product with opposite signs, so they're going to cancel. And then, of course, multiplying positive root x times negative root x, we get a minus x dx. And all of a sudden, something very nice has happened. We have x plus 1 to the half power minus x to the half power with a 1 in the denominator dx. Now, integrating this is pretty straightforward. We have x plus 1 to the 3/2 power with a 2/3 in the front minus x to the 3/2 power with a 2/3 in front plus c. Number 18, the integral of x over square root 7 minus x to the 4th dx. Let's go ahead and start off with u sub. If we let u equal x squared, du will be 2x dx, so we can put half a du is equal to x dx. Now this integral becomes 1/2 the integral of 1 over the square root of 7 minus u squared du. At this point, you might be tempted to jump right into trig substitution, which will work, but also notice this is just sine inverse. So this is 1/2 sine inverse of u over the square root of 7 plus c, bringing back our x squared, and we have it. If you choose to do a trig sub, you would let u equal root 7 sine theta and go from there. Number 19, the integral of 1 minus sine x over 1 plus sine x dx. So it sure would be nice to do some substitutions here. If we just let u equal sine x or 1 plus sine x, we don't have any cosines. It would be even better if we had a sine squared or a cosine squared. So let's go ahead and take this integral and multiply by just the right quantity that will allow us to use a Pythagorean identity. In other words, let's multiply the bottom and top by 1 minus sine x. So in the numerator, we get 1 minus 2 sine x plus sine squared x all over 1 minus sine squared x dx. Bottom becomes cosine squared x. And now let's split this up into 3 integrals. So our first integral is 1 over cosine squared, which is secant squared x, like that, minus 2. We have sine x over cosine squared. Well, off to the side real quick. If I have this, right, that's what that middle term will become in the numerator when it's divided by cosine squared. And this is tangent times secant, or secant tangent, which we like that antiderivative. And then finally in back, we have sine squared over cosine squared, which will give us the integral of tan squared x dx. Here we just get tan x minus 2 secant x plus tan squared x is the same as secant squared x minus 1. And here we get another tan x minus x plus c. So we end up with 2 tan x minus 2 secant x minus x plus c. Number 20, the integral of ln y over y times the square root of 2 plus the quantity ln y squared dy. This one can be dealt with several different ways. Probably the most common first attempt is to let u equal ln y, and that'll get you there eventually. But I want to see what happens if we let u equal 2 plus ln y squared. Let's see what happens here. So du, derivative of 2 is 0. And then here we're going to need to use chain rule. So we're going to bring the 2 down in front. Ln y stays the same. And then we're multiplying that times 1 over y, the derivative of the inner function dy. And if we multiply both sides by a half, you immediately notice that we have an ln y in the numerator, a y in the denominator, and then there's our dy, which is exactly what we have here, here, here. And so this integral simplifies really nicely. In other words, we have 1/2 the integral, the ln y in the numerator, the y in the denominator, and the dy all become 1/2 du, and we're left with 1 over the square root of u. And that's it.